Morning. I'm Balachandran. First of all, I want to thank Prof. for inviting me here to share some of my thoughts on the sustainable energy system. And when I asked him, என்னப்பா பேசுறதுன்னு கேட்டேன், அது வந்து he selected the topic. Why don't you talk about the materials for sustainability? So I have collected my thoughts and I'm going to try to share with you. So please put up with me for an hour or so. And you can give any time you want. I won't feel bad. And you can also take a nap. Everything I'm going to say is only meant for the young researchers and the junior researchers here, not for the mature professors, because they probably already know. Okay? And as Professor said, sustainable development is not about us. It is for the living earth for the future generations. Okay, the world is just like we are renting this space, that's it. So after we need to clean it and we leave it for the next generation. I need the future generation. That is what sustainability is. It was already explained by Professor Ramesh Kumar. I retired from Alba National Lab after 40 years of research in 2022. Any problem? Technical problem? Everything fine? Okay. And let me just quickly share about me. I completed my undergraduate regional engineering college at Trichy in 1970-75 batch. Did my metallurgy as Professor mentioned because it's now very important. The reason why I went to metallurgy is so that because my mother didn't want me to live on this state. Shab steel plant was coming up at the time, so that I can stay here and then leave again. That was the primary purpose of me entering into metallurgy. But the fate has different routes. So that's what happened for the last 50 years. And then I went to Institute of Science where I did my MD and left India almost 50 years ago in 1977. I finished my PhD in material science and engineering in 1980, and since then I've been working in energy related materials. All this time I've been working on perovskite structural materials. Okay, all the areas that I work have some connections, and I will tell you in the next slide what it is. So I retired from the paid job in 2022, and then I've been doing voluntary work to keep my brain cells active for some more years, God willing. So that is about me. I am from Salem district. My native place is not too far, it's called Jalandapura, near to dam. And I speak Tamil and I assume that most of you here understand Tamil. Okay? So that, let me just tell you about Argonne National Lab. Argonne National Lab is the US Department of Energy Laboratory and it's the first national laboratory in the United States and it was designated as a lab in 1946 and we are situated about 40-45 kilometers southwest of the city of Chicago. And we have all kinds of research going on. The most important one is that is where the nuclear controlled chain reaction started. Okay, that started in 1944. Then the result is the end of the World War, as you all know. The person standing there, that is a Fermi. This is the Fermi. We must have studied Fermi in physics and chemistry and whatnot. So that is Fermi and Manhattan Project leaders are there. You must have also watched or heard about the movie Oppenheimer. The real Oppenheimer is the one right here. Okay? So that is the birthplace of chain reactions, originally meant for peaceful process, but you know, the rest is history and so on. So that is about Argonne National Lab. And now about me, my research areas all around for the last, 50 plus years, I have focused and worked on all these. Okay, fuel cells, hydrogen technology, separation, production, okay, natural gas conversions, superconductors, ceramic capacitors for electric vehicles, electrochemical production of chemicals, and graphene used copper materials, solid state batteries, and the so-called ultra-fast sintering of materials. Never these materials. And about more than 90% of all these things are based on ABO3 structure, so-called perovskite structure. I am sure you must have studied BCC, FCC, FCP, and so on in your material science. I assume that you have studied, right? Okay, so this is the ABO3 material, and that's my focus. So now there's a disclaimer before I get into my main talk. I want to show you what is the typical life cycle of a researcher. Okay, typical life cycle of a is considered. Typical life cycle of the research. Not citing that, no problem. Okay, this is the scientific content. This is the time in years, not to scale, just it's systematic. Because the slope will change depending upon individual person's interest. So don't worry about the slope. So basically, you first, as you do your research, you have first contributed paper in a national meeting or a conference, right? A workshop. That's how we start, correct? So in my case, that actually started in 1974. Probably before most of you were born or your parents were born. I don't know. And then, as you progress in your career, you will be invited to give an annual talk in a conference. And then you will go and then give, plenary talks. Okay, then you will give keynote talks and so on. You will get awards like what presented. You will get a nice car and all those things. Okay, that's more or less that's the peak. Then it starts coming down because it's a career is going to end and so on. Then you at some point you begin to talk to yourself because nobody invites you because you are gone and you are not active and so on. And you will probably be invited for after dinner talk because no one cares about science, right? You just go there and talk about something and then get away. So that is okay, fine. But the worst part is, if that continues then you start, no one wants to invite you for dinner talk. Then you start talking to yourself. You stand in a mirror or after bathroom, shower, and then you talk to yourself. And that is the worst part because then you get into trouble with your wife. Because when you talk to yourself, then he thinks that you got crazy. Then you have to be afraid because there's always a person in the house with a single, right? And with a single, which is a white one. Okay? So then he will start hitting you with the purikatai, okay? That's the single. And you don't want to get into that state, okay? And so that's why they like to extend the slope. And And then finally, you just, your life is over, you get buried 6 feet, okay, under the ground. So that is that no matter what it is, it's a typical life cycle of any researcher. The slope can vary, and the person with the symbol can change, but the whole trend will never change. So, what I am trying to say is that what I am going to share with you now may not be my own research, it's all the information I gathered and then stuff that I did or my students did in for the past 50 years and so on. And then some additional new things that I have added. So now I have come to the main presentation with that kind of disclaimer. Okay, the reason I am telling is I am in that slope, so if you ask me some questions, I may not be able to answer everything, I may forget. So at my age, I am lucky to remember why I am in that slope. In this case, I am lucky to remember that Dr. Sangapan sir has asked me to talk about materials. So that itself is a blessing to me, and I want to make use of that opportunity. So what I am going to talk to you is for young researchers and students here is the energy scenario in India. Because why are we doing this in the energy department? So what is happening in India? What is the impact that the business has this world? As we said, if you don't worry about sustainability and continue life as is, what is going to happen? I want you guys to see, get a much broader picture. And we can change that. So what can we do? So they have come up with all the new technologies, electrification of the transportation system, electric cars, electric trains, now airplanes and so on. And then we all talk about, all our people what we talk about reduce, reuse, and recycle, as Prof. also mentioned. Then we do a lot of work in hydrogen technology. So I want to give you, mention that, but what I want to say is, what are the challenges and opportunities involved? I'm not here to say that America has done this, Germany has done this, Australia has done this. No, that's not why I'm here. I want to see what are the challenges that lie ahead for the young researchers here so they can select as a topic and focus on research and then do it because as the Tamil movie says, you can do that. That is the purpose of my talk here. We talk about opportunities or the challenges involved. And then for the researchers, I will try to present the takeaway message. Now coming to the energy scenario in India, what I brought you here is taken from the energy statistics of India 2025 report. Okay, so all the references I have given, you guys can take it and read further. What I have shown here is how the energy use in India has jumped for the last 7 years, from fiscal year 2015 to fiscal year 2025. 24, I'm sorry, 2024. We started with about 28,500 petajoules. 1 petajoule, as you know, is about 1 lakh, because I'm India, and we convert into lakhs. So it's 1,72,000 barrels of oil a day. That's kind of 1 petajoule. Okay, I'm sure you know what the joule is. So it is a 10 power 15 joules per petajoules. And if you want to put it in oil, in terms of oil, it's 1,72,000 barrels. And how much is 1 barrel? 1 barrel is 159 liters. So you can multiply how much of energy you are talking about. That is what it is. So if you use a lot of energy, and it has jumped by about 35% over the last 9 years, yes, that's good one sense, because that means, that's why I asked whether everyone understands Tamil, because energy use is really a good indication for the progress of the nation. That's what you want to see. You don't want energy to decline. But what you want to see, focus is where the energy source, what's the energy source? How do we get that energy? See, that is where the main problem is. It is not an increase in energy, okay, use of energy. It is how and what the source of the energy. So let us dive into it. Take a deeper dive India's energy consumption. We are the 6th largest energy consumer in the world. Okay, and three-fourths of India's energy needs are made from water energy. By that I mean coal, gasoline, natural gas, petroleum, and so all carbon, hydrocarbon. Okay, that is where the three-fourths of energy comes from. And we consume, as I said, lot of electrical energy. about 1,900 terawatt hours. We are third in the world. We consume that much. In India, we consume crude oil about 55 lakhs in a single day. In India, we don't have crude oil reserves, as you know. Everything is imported, and also it is coming from very sensitive countries, and things are changing every day. Every day. Okay, with the tariffs and so on. So we import 48 lakh barrels. 1 lakh, 1 barrel I said is 159 liters. So you can calculate huge amount of oil we import. If you put a dollar or Indian rupee number for importing, at the cost, when I checked the oil price, is about $57 a barrel few days ago. And there's 90 rupees for a dollar conversion that keep changing every day. That means that translates into about 2,500 crore rupees in a single day. That is what it costs for Indian government to get all that oil. 2,000 means 2,500 crore rupees in a single day. So now you can think where your GST and yes, GST and all those things go. See, that kind of money is here because you don't have that resources. So that's the one point. Number two is that we are consuming these hydrocarbons at a much faster rate, million times at faster rate than what it took for the nature to create by endothermal reaction process. Okay, to go on. So by doing so, hydrocarbons, we are emitting too much of CO2. In fact, we are emitting almost 3,000 million metric tons of CO2 annually. That was about 2 years ago. 3,000, okay, million metric tons. When I talk about metric tons, this number, that number means nothing. Let me give you a perspective. Let us consider what is 1 ton of CO2 under STP conditions. The 1 ton of CO2 in STP conditions, we can fill a balloon that is 10 meters in diameter. 10-meter diameter balloon can be filled with 1 ton of CO2 under STP conditions. I'm talking about 3,000 million metric tons annually. Okay? Or you can think of the box that is 27 cubic feet. That is 1 ton. Now, let us correlate that into Meru Dam. We are from near Meru Dam. You know Meru Dam full capacity, like article when you go there, and it's overflowing. Okay, it is 93.5 TMC, 1000 million cubic feet or billion, 1000, that's billion cubic feet, 93.5 million cubic feet. That's a huge dam. You know the volume at 120 feet. Right now it is about 92 feet. Okay. So, you know how much of the CO2 tons we have been emitting. We can easily convert that into volume, right? You know all these things. I don't have to explain that. So let us look at it. So the nearly 3,000 million tons of CO2, the volume India has given how many of TMCs. I know I also mentioned the capacity of Metro Dam, which is 93.5 TMC. Right. So what I am telling is that carbon dioxide emitted in 1 year, that is in 2023 itself, we can refill Metro Dam to full capacity 620 times. Okay, almost twice a day we can empty and then fill it with this balloon. See, that is the amount of CO2 that we emit. Simply talking about the tons and so on means nothing. Now we can get an idea. So how much of CO2 you are emitting. Another way of looking at it is that you can look at the map and you know the area of India. We know the volume divided by area. What it says is that the amount of CO2 that we emitted in India in year 2023 means we can think of the entire area of India covered with a blanket. Okay, entire area of India covered with a blanket that is 47 centimeter high. In other words, nearly half a meter high blanket is covered, entire area of our great nation. That is how much CO2 emitted in 1 year, and it is increasing. Okay, so you cannot afford to continue